Hello, do you see this rubber band? Do you see this spring? I will tell you why I have taken all these things. See, if I apply external force, if I just stretch it, I can see that there is extension of the rubber band. And if I apply external force this side, I can see that there is an extension of the spring. So can I say that these two bodies are elastic bodies? And answer is yes, of course. So whenever there is an external force applied to bodies, when there is a change in configuration, it could be shape, it could be size, whatever. Whenever there is a change in configuration, then I can say that there is an elastic body. Remember, when I remove the force, you see here I've got a rubber band, as I told you, apply force, extension. When I remove the force, it will come back to the original position, right? Original configuration. And it happens in the case of spring also. So there is an extension of the spring when I apply external force. When I remove the force, it comes back to the original position. So I can say that it's a purely elastic body, and when I remove the external force, it comes back to the original position or configuration. So that is an example for elastic body. How about a plastic body? See, when you apply an external force, there is a change in configuration. But when you remove the external force, it doesn't come back to the original position. It doesn't regain its original position. So I can say that those bodies are plastic bodies. So in classical mechanics, when you apply the external force, there is a motion, right? There is a change in acceleration. So that is purely a rigid body. Those sort of bodies are purely rigid body. Whenever there is an external force, no change in shape, no change in configuration. So I can say that those bodies are rigid body. But these things, elastic bodies, plastic bodies, are not rigid bodies. When there is an external force, there is a change in shape. So that's what I'm going to discuss right now. Now, as I have got a rubber band here, let me say I have got a rubber band, a straight rubber band of length L, capital L. I'm going to apply some external force. I have to stretch it down. It could be done by gravity also. I have to hang some weight at this point. When weight is just mass times acceleration, that will that's what the weight force is done, right? It is going to do some work here. So I can pull it down, or I can suspend some masses. Both are the same cases. So when external force is applied to the any elastic body, there is going to be change in size or shape or configuration. For example, right now there is a change in length. The initial length was L, and there is a change in length, very little. It could be something like for 1 meter, it's around like 5 centimeters if it is a case of rubber band for some amount of force. So what happens is, here, whenever there is an external force applied to the elastic body, there is a change in configuration. Now it is in terms of length. So additional length is, being got here. There is an external, then additional length, small L. So I'm going to define two factors here. One is stress, another one is strain. Both look same in natural life. You say, I'm stressed, I'm strained. But in physics, these two parameters are different. I'm just going to tell you how it is. So I'm going to define what is a stress here. Remember, when I apply force, that force is applied to the certain unit area cross section. So whatever the amount of force you have got, that is per unit area of cross section, is a measure of stress. So more and more force you apply for the unit area, more and more stress you get. Or if you apply more and more force for the very little area, I can say that you're going to apply more and more stress. So stress is inversely proportional to area with which you apply the force, and also directly proportional to the amount of force. So that is a stress. So if I have more and more weights, more and more stress I get it. Another side I've got a strain, which is purely dimensionless. If I go back to the stress, the unit of stress is force per unit area, Newton per meter square. How about strain? Strain is technical word which is defined as the change in length by original length. So whenever there is an external force applied to the body, elastic body, there is a change in length. Additional length is small L. So the change in length to the original length is going to be defined as the strain in elastic body. However, it doesn't have any unit, and its evidence is length by length in dimensionless quantity. And what Hooke's law states is, if I apply more and more stress, I would get more and more strength. So this is an example for elastic body, as I told you before. It's a spring, and if I apply 2 Newton of force, I'll get some extension. More 4 Newton, again some extension. 6 Newton. So there is going to be a linear relationship between the amount of stress I apply and the strain I get. So for equal forces, I would get equal change in length. That's how this Hooke's law. But remember, this happens only within the elastic limit. There's some limit, if you go beyond the limit, this Hooke's law doesn't valid. I'm not telling that there won't be any extension. There will be extension, but Hooke's law doesn't valid. I'm telling you that there is no linear relationship between stress and strain. But what Hooke's law states is amount of stress is directly proportional to the strain. That's how the linear relationship between stress and strain exists. And remember, when I've got this proportionality constant, proportional I've replaced by a constant here. This time I'm going to replace by a constant that is called elastic constant. This time I've defined as Young's modulus times strain. Where Young's modulus Y is just stress by strain. Stress is just force per unit area. Strain is small length by original length. So this is the formula for the Young's modulus. So for the particular elastic body, the Young's modulus value is a constant. It doesn't matter how much force you apply. It doesn't matter how much extension you get. For equal change in force, if you equal application of force, you'll get equal change in length. And that's the Young's modulus defined here. So it is just independent of the force and the length, even though the factors are here, ratio, however it remains constant. For the particular given elastic body, the Young's modulus value remains constant, it doesn't change. It only depends on the nature of the material. For example, if the material is very stiff, I can say that there is not that much extension or change in length. When there is no change in length, strain is very less. When strain is less, Young's modulus is going to be very high. So for the particular material, if the Young's modulus value is very high, I can say that that particular material is going to be very stiff. It's not going to be very soft. So if I compare the Young's modulus values for the rubber and the steel, I would get Young's modulus value for the steel is very greater than the rubber band, and because there is a more extension for the rubber band rather than in case of our steel. So all depends on the amount of strain and amount of the stress you apply. So Young's modulus of the material, it depends mainly on the nature of the material. So this is Young's modulus. Again, it has the same unit as the stress because the strain doesn't have any unit. I don't have to worry about it. This is just the Newton per meter square. Now I'm going to tell you something great. What I'm going to do is, as I've done it last time here, I've got a rubber band here, one side, I'm just pulling it down. I have to apply some force, right? When I apply some force, there is something work to be done, right? I cannot simply do it without doing any work. I have to do it, right? So when I apply some force, external force, there is something work done, right? That work done will never go wasted. Somewhere it will be stored. So that work done is stored as elastic potential energy. I'm going to find out when I stretch a rubber band, how much work is done, how much potential energy is stored. That's what I'm going to discuss right now. So here I'm going to discuss about energy. There's elastic potential energy stored in elastic body. And it could be rubber band, it could be spring, or it could be any elastic body. It's not a problem. Now, I've got a Young's modulus equation. Y is equal to F by A times L by small l. And I'm going to write for F here. This equation represents F is equal to Y A small l by capital. This is an expression for the amount of force you apply, which is just depending on the factors area of the cross section where you apply the force, and length, the capital, that is extension, and this is original length, and capital Y is elastic constant or Young's modulus of the particular elastic body. So this is the amount of force you apply for the unit area of cross section for the extension of length L for when there is original length capital L. So let me say, dl is a very small displacement for the applied force. Whenever there is extension of the wire, so dl with a very small change in length, there is amount of dl. And I'm going to find out how much work is done, that is for the small displacement dl. So that's work done is equal to the dot product of force and displacement. There is a not out here. So that's how the work is defined. It's a scalar product of two vectors. There's a dot product of force and displacement. Remember here, I'm just going to apply the force in downward direction. Displacement and extension is also in the same direction. So the angle between F and dl is just purely 90 degree. So case 0 is just equal to 1. So I don't have any problem in writing magnitude of F, magnitude of dl, cos 0 is 1. So I'm just writing F dl. I'm going to substitute for F here. So d omega is equal to F is just y, capital A, small l by capital L, dl. This is the small work done in extending the rubber band or an inelastic body for small displacement dl. But my intention is to find out what is a total work is done for in extending this elastic body from 0 to L. So total work done in extending from 0 to the full extension length L. So that is W is equal to integration of 0 to L. This is dW. That is 0 to L. dW is capital Y, capital A dividing by small capital L times small l times dl. Remember, Young's modulus for the particular elastic body is just a constant independent of time. And I'm going to take it outside. Area is also constant. Capital L is also constant. So integral of L dl is just L squared by 2. Limit is applied from 0 to L. I'm going to write as it is 0 to L. So work done is equal to capital Y, capital A dividing by L. L squared by 2 minus 0 squared by 2. So I've got this expression on. This is the amount of work done by the external force, or I can say that it is a restoring force. Remember, when I apply the external force, there is something called a restoring force which tends the body to regain its original position, which is always acts opposite to the external force. Right? So that's why. So work done by the external force, that is what meant by Karthik, is exactly equal to work done by the restoring force. So that's the work done is this amount here. Remember, when since spring force is is a conservative force, it's independent of the path. Work done is independent of the path and only depends on initial and final position. I can say that whatever the total work done is exactly equal to potential energy stored. That's what I wanted. I find out how much amount of potential energy stored in the spring. So that is potential energy is equal to YA by capital L, but this is 2 times L squared. I'm going to multiply small l and capital L. I'm sorry, I'm just going to multiply capital L, that is the length of the original length of the elastic body, and divide by the same to do some manipulation here. So this Y into L squared, this A into L, area into length is just volume of the wire. I'm writing here dividing by 2 L squared. So this potential energy is equal to, there is a stored energy in elastic body is equal to 1 by 2. And I'm going to write this is Y, this is L by capital L whole square times weight. This is equal to half into Young's modulus. Yes, this is Young's modulus. Y is defined here. L by capital L is just a strain. So I can write it is a strain square times volume. So I can find out the amount of energy stored per unit volume. So there is a potential energy stored per unit volume that is equal to, so I have to divide by volume, so that is half into Y into strain whole square. So volume gets cancelled because I'm finding out the amount of potential energy stored in elastic body per unit volume. I can write this same expression in terms of stress also. I know that Young's modulus is equal to stress by strain. I can write the expression for Young's modulus here. There is half stress by strain, this times strain whole square. So that is equal. So one strain cancel. So half into stress into strain, which is an expression for the the potential energy stored in the elastic body in terms of the stress and strain. So thanks for watching this video. Come back to you next time.